Hello, everybody. I'm here to talk about how Schibsted collects 800 million events a day. And I think probably at this point, most of you are going, Schibsted, who's that? Events? What's that? Why? So we're going to quickly go all the way back to the beginning and explain what it is I'm talking about. Schibsted, which I think probably none of you know, is actually a global internet giant with something like 200 million users a month, 20 billion page views a month. We own the biggest newspapers in Norway and the biggest newspapers in Sweden. And then on top of that, we have internet marketplaces like Blocket in Sweden in 30 different countries. So the company basically started with the newspapers, and then they moved the classified ads out of the newspapers and onto the web, and then they grew that part quite dramatically. So the last few years, the media houses have been bleeding money, basically, and the marketplaces have been almost printing money. So the normal thing that you do in this situation is that you get rid of the loss-making part, and you concentrate on the part that's making money. And if you don't do that, the chances are that somebody will buy your company and do it for you, and thereby make profits when the share prices go up. That is out of the question for Schibsted, because Schibsted is actually a 180-year-old company. It was family-owned until about 10 years ago. So the last person in the family to inherit the company was this guy, Tinius, and he was a newspaper man. He took over a failing newspaper in Norway, Verdens Gang, VG, and he turned it around into the biggest newspaper in the country. He was quite passionately devoted to the role of newspapers in society, basically. So when he realized he wasn't going to live much longer, he turned the company over to a foundation. So the foundation is run by a board of media people, and the purpose of it is to ensure that Schibsted continues to deliver independent news. Whether that's going to work or not, we don't know, but it does mean that getting rid of the newspapers is out of the question. That's just never going to happen, because the whole point of Schibsted is to have the newspapers. So what we're doing instead is to restructure the company. It used to be so that every site, both the newspapers and the marketplaces, were totally independent. So it may sound like I'm joking, but Schibsted actually did develop 30 different internet marketplaces as separate code bases. In fact, when they set up a new marketplace in a new country, they would typically ship the source code for Blocket on a CD-ROM and say, off you go, guys, build a marketplace. This was because Schibsted didn't see itself as a technology company. And that's now changed. So now all of these sites are going to switch over to common components. That's a process that's already started. And we're going to build things only once. And the part I'm going to talk about is the bottom box on the left here, data and analytics, because key to the new Schibsted strategy is using the information that the users provide us with. When you have 200 million people using your sites every month, that actually gives you quite a lot of data. So the event collection that I'm talking about is basically, when you visit Aftonbladet or Svenska Dagbladet or Blocket, your browser is going to send a JSON event to the system that I'm talking about here, saying that this user looked at this page with a browser that was this big and blah, 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 blah. All of that stuff. And this then gets crunched by data scientists. They use it to decide what ads to show you, for example, because we can charge more for ads if we can say, we're only going to show this ad to women aged 20 to 40 living in Stockholm, right? Normally, you just show the ads to everybody, but a lot of ads make absolutely no sense for a person of the wrong sex or stuff like that. So we can charge more for the ads that way. We also do recommendations so that you can subscribe in the newspaper and say, send me articles I'm interested in. And then the system just learns what you're interested in from what you do. So this is the number of events per day for the last couple of months. You see the weekly pattern, right? And you see one more thing. That's Christmas Eve. Not many people online. And this is the New Year. If we break it up by site, I can see when people in France eat dinner. I can see when people in Malaysia wake up and stuff like that. If we did this by hour or even by minute, you could see that around midnight on New Year's Eve, the traffic goes and then back up again. And sometimes when we look at the dashboard, you see the traffic spiking, and you know that somewhere in the world something happened. In this case, it was a helicopter crash in Western Norway that made the traffic on the Western Norwegian newspapers multiplied by 6. It's enough that you see it here on the global view as well. Sometimes when this happens, we see that it's the Swedish newspapers, and you open the Swedish newspapers, and you realize that although you live in Norway, you don't know the Swedes as well as you thought. Because you look at the news items, and you go, one of these is a big deal, but I have no idea which. None of it makes any sense to me. OK, whatever. This was the business part. So now we're going to go into the technical stuff. How do we actually do this? Starting on the left, we have 3 tracker implementations. This is basically the code that sends the event. So it's implemented once in iOS, once for Android, and once in JavaScript. These guys all send their events to an endpoint that we call collector, which runs in Amazon Web Services in Ireland. That writes it to a Kinesis stream. I'll come back to Kinesis afterwards. And then basically the data is fanned out from there. So the piper and the upper part there, that's real time, or real time-ish. It delivers the events within a few seconds. The lower part is where we batch up the data by an hour and compress it so that it's more efficient to process. It looks pretty simple like this. Unfortunately, it's a good bit more complicated. For example, I left out the ID system that's called sys. So actually, the first thing the tracker does is it starts batching the events. It can't send them yet because it doesn't know who you are yet. And then it makes a call to sys, and sys looks at your cookies and sends back your ID. And it may talk to the Schibsted ID system to find out who you are. And then once the tracker knows who you are, it will send the events. But there's one complication here, and that is that in SPID, you can go into your user account and you can say, don't track me. If you do that, sys will tell the tracker that this user opted out, and we won't send the events. And that's actually why we have this complicated system, because really what we should be doing is we should just send the events to the collector, and collectors should take care of the cookies and all that stuff and talk to sys so that the tracker doesn't have to wait. So we came up with this idea, we can make everything much simpler, and then we realized that at some point, some user is going to opt out, and then he or she is going to look at what the browser does and see that, hey, I opted out, but they're sending events anyway. Of course, we would throw those events away, but who would believe that? So we're doing it this way instead so that people can see that we're not tracking you. The step behind Kinesis here writes to something that's called S3. That's an Amazon service that's it's like a file system over HTTP, basically, with the benefit that there's nothing called disk size. That concept doesn't exist. You write as many terabytes as you want, and they stay there. They never go away. The trouble is we can't write to S3 directly because latency is relatively high. So it's a long time to wait before the batch of events is safe. And it also means that if we have to go back and forth to S3 a couple of times, the latency gets quite high. So that's why we have Kinesis, which is much faster. Each event is about 2,200 bytes of JSON, which is not really a good idea, but that's the way it is right now. So that comes to almost 2 terabytes per day of data. Loading this from lots of small files in S3 turned out to be very, very slow, to the tune that you would come to work, you start up Spark, and you say, I want to load this data set, and then after lunch, you can start processing. So we changed it. We now use something called Parquet. And this is what the hourly compression does, and that's a column-oriented binary format, much, much faster and much more compact. Unfortunately, a little complicated to turn JSON from 40 different websites with slightly different structure into a database-like format. But that's been taken care of. We also break the data sets up into 2 versions. So one is anonymized, meaning we take out the last part of the IP address, we jiggle the timestamp a little bit, and we take away the user ID and stuff like that. And then the other data set is identifiable. There the identifiers are all there. The reason we do this is that now we can give a lot more people access to the anonymized data. They can still do a lot of valuable analysis, even if they don't know who the users are. So it makes the data more available internally, basically. Whereas access to the other data set, that's quite hard. That requires you to go through paperwork and a lot of stuff like that. Yeah, this gets used for recommendations, ad targeting, business intelligence. It goes off to the individual sites so that they can do their own statistics. It's also used for dashboards so that the journalists can see how many people are reading their article in real time and stuff like that. There's even events to show how far down the page the user goes. So the journalist can see a view of their article. Where it goes dark as more people are leaving the article. So they can see where people stopped reading and stuff like that. All of this runs in AWS, like I was saying. So in fact, it's relatively similar to what the previous speaker was showing. But I think not many of you were here for that, so we'll go through it. If you want to deploy something to AWS using their servers, you have to make an AMI. That's basically an image of a Linux machine. So you run a script to set up the machine the way you want it, and then Amazon will save what the machine looked like. And then you say, OK, I will make an auto-scaling group that will run this machine image, and I want 2 to 75 nodes. And then you set up some scaling rules. Then you put an ELB in front, and off you go. So here's a screenshot from the tool called Ask, right, which we're using to administer this stuff. You can see on the left here that we have auto-scaling group number 59. I've set it to between 7 and 30 nodes. And you can see that this was taken early in the morning when traffic is coming back up. So you can see that it had 7 nodes in service that were running. And then when I took the screenshot, it was starting the 8th one because it had decided that it needed more nodes. And this is done based on the scaling policies. So here we have a rule saying if we're using less than 20% CPU, stop 1 node. And then there's the cooldown of 10 minutes. And then if we're still below 20%, then shut down another one. If CPU is above 65%, then start another. We could, of course, say 99% or something like that, but the reason we don't do it is that suddenly there are spikes in the traffic. We had one case where one of the newspapers deployed a new tracker that would send an event every time there was a scroll event on the page. So within 10 minutes, our incoming traffic had doubled. If you're then already running at the margin, that's not going to go very well. So you have to leave some leeway. And then the last one here is a panic rule. If we're below 4 machines, go to 15 immediately, no matter what. Yeah, you'll see why later on. We use metrics quite a lot. We're using something called Datadog, which runs a little service on each node, which collects the OS statistics. And then in the code, we have little counters that also report metrics to Datadog. And this is great because when you're writing code, you're making a buffer, for example, or a queue, and you're always wondering, so when the system runs, how big is this actually going to be? With metrics, you put in one line that periodically just measures the size and sends it to Datadog, and you see the upper left there, that's my queue size. I can see it by minute if I want to. I can see how it's changed over the last year. And as you will see later on, when things go wrong, this is extremely useful because this allows you to look at the code when it went wrong and you can see what it was that was actually happening. So the great thing about this is if you know the system well, you can just look at the dashboard and you know what the code is doing. You know exactly what is going on. Extremely useful tool. And once you have these metrics, you can set alarms on them. So we have an on-call system. Here's an alarm that says if more than, 2% of events are missing after 1 minute, call PagerDuty and have the on-call person's mobile phone go off. I will wake them up even if it's in the middle of the night, and I'll have to come and fix it. Tuning these is a bit of a black art, but really gives you very good control. Unfortunately, the metrics from the systems themselves aren't enough, because even though all the systems are running and everything looks good, that doesn't mean the events are going where they should. So we have another system called Probe, which every second will inject one event, and it puts ID numbers in these events. So when it picks them up from the other side, it can see exactly how long it took for each event to go through the pipeline. It can see if there are duplicates and if there are events missing and that kind of thing. So here on the dashboard, you see the yellow thing there. That's showing how many events didn't arrive after 30 seconds. And you can see that sometimes there's an event or even 2 events that takes more than 30 seconds. When things go wrong, suddenly these curves go whoop, like this, and then you know that, uh-oh, somebody has messed up something somewhere, and you have to dive in to find out what's going on. Yeah, if we look a little closer at the data collector, that's basically the most vulnerable part of the pipeline. The trackers that run in the web browsers, the moment the user clicks to another page or closes the tab, they're dead. So you can't rely on the client to resend. Right? You got the event, now you have it, and now you have to save it. Otherwise, it's going to disappear forever. And when the event is in the collector, it's not on disk anywhere, not yet. So the thing the collector absolutely must do is to get stuff to disk as fast as possible. And of course, also deal with the spikes and stuff. So because of that, we made it as thin as we possibly could. It does very, very little. And that's how we're able to scale it. And the reason we rise to kinesis is that a kinesis write takes less than 1/10 of a second, usually. And that means that's 1/10 of a second until stuff is on disk and it's safe. And the way kinesis can do that is basically by being extremely simple. It's just a stream. It's like Apache Kafka. It's just a sequence of binary blobs. That's all. But that's also all we need. The data collector itself is written in Scala. It's based on the Netty web server and uses 2 frameworks made by Twitter called Finagle and Finatra. Usually when you overload a web server, everything works fine until you hit this point where it can't take any more, and then everything just melts down and it stops working. That doesn't happen with this system. If you overload it, it will open more incoming connections than it can handle, but everything will process just fine. But the number of open connections will grow and grow, and then eventually you hit the OS limit and things stop working. But it's very, very well behaved. You can load it as hard as you want, and it's not going to misbehave. So the first design that I did was like this. It was just to try it out. Here, we get the request, we parse the JSON, we do some checks, we add the timestamp, IP address, and stuff like that. Then we write to Kinesis. We wait until Kinesis is done, and then we send a response. This doesn't scale at all. Now we were running with 7 to 12 nodes with a lot of margin. With this design, we'd have to run, I don't know, 70, 100 nodes. And the reason is, of course, that we're wasting a lot of time there, right? Waiting for kinesis. That's one thing, and the other is that writing each event individually is very slow, right? If we can batch them up and write a whole bunch at the same time, it's much more efficient. So the first version that we actually deployed looked like this. The request handling thread will do all the stuff to the JSON, put it on the queue, and then just tell the client it's OK. But it really is OK, we don't know, but the client isn't going to resend anyway, so who cares? It doesn't matter what we tell them. And then there's a separate thread that will take the entire queue, send it to Kinesis, wait for the response, and then just grab the whole queue again. Take all of it. And this is it's pretty much the version that's running. This scaled very well. It's also very simple. But this is when everything's working fine, right? When you're working in a distributed environment, you don't really know that everybody else is going to behave well, right? The trouble was we didn't really know what kinds of problems that this application would hit. So we had a lot of discussions where people were saying, oh, I heard that sometimes some of the nodes won't be able to talk to Kinesis, but the other ones will. We never found any evidence of that. We didn't really know what the errors were going to be. So in the end, we decided adding this complexity to deal with problems that we don't know if are real, that's risky. Quite often, if what happens is not what you expected, these workarounds wind up causing problems instead of solving them. So we just let it run. It took about 3 weeks, and then here is the metric that we create for how long it takes to write to Kinesis. So you see, up until 11:14, everything's good. The writes are really, really fast. And then suddenly they start taking 5 to 10 seconds, each individual write. And what happens is that now we're suddenly receiving more events than we can write. So the queue grows. And the queue is just an array list, so stuff accumulates in memory. And then you can see here that problems start at 11:14. Around 11:26, we're dead. The whole thing has gone down. Which is a little disappointing, because what actually happened? We're not doing any more work, right? We're just accumulating more data than we can send. So why does this take down the service? Well, it turns out that the CPU is being overloaded. And the reason it's being overloaded is that we keep adding more and more stuff to this queue. And this is parsed JSON, right? So it's lots and lots of little objects. So the JVM wants to increase the heap size. Before it does that, it will do a full GC a couple of times. That takes a lot of CPU. And then increases the heap size, and then it turns out that, hey, 30 seconds later, you have to do everything all over again. So basically, doing the GC is killing our service. And that's not even the end of it, because when you analyze this incident afterwards, you see that after the Kinesis writes start being fast again, the system doesn't come back. And when I looked at the logs and really did the analysis, what I see is something I called a rolling failure. So you're in a situation where all of the nodes are dead, but Amazon knows you want 8. So it tries to start them. When the first one comes up, it's now receiving all the traffic. It lives about 30 seconds, and then it dies. So it dies before the next one comes up. So basically, you have all these nodes being started up, living 30 seconds, dying, and then just rolling like that. So the reason the incident ends there is that in a panic, I just doubled the size of the autoscaling group. You get enough servers starting at the same time, they manage to offload each other, and it's OK. And then everything runs smoothly after that. So all this stuff comes from the incident report that we did, where we went through, OK, what went wrong? What could we do? Eventually, we did a redesign where the request thread now hands off the JSON to this converter thread the converter thread will turn all these little objects into a byte array. It serializes the JSON. The reason I do that is that now we spend much less time on the GC, right? Because the structure that we have to GC is much, much smaller. There's one object instead of 300-400. Then it goes to the same kinesis writer that we used to have, but now the queue is fixed size. So if you try to give an event to the writer and the queue is at 5,000, which is the max, then the writer will hand it off to the next one. So we had already a kinesis stream in Ireland, which is where the application is running. And now we set up another one in Frankfurt. And the second kinesis writer is writing to Frankfurt. So the reasoning was that, well, if they have trouble in Ireland, the one in Germany should be OK. So most of the time, the second kinesis writer is doing nothing. It sleeps like 100 milliseconds, wakes up, oh, queue is empty, goes back to sleep. But when there's a crisis, the events will spill to the second writer, and it will start sending them to Frankfurt. And what do I know? It could perhaps happen that they could be down both at the same time, right? So we made a fallback, which is the spillover queue. That will just take the events and write them to disk. And then there's a thread that looks at the two other writers to see, do they have room? And if they do, it will inject the events back in the stream. So basically, we will use the disk as temporary storage until things cool down again. And we didn't have to wait very long before we get another latency spike. And here you see that the queues are capped out at 5,000. It never grows more than 5,000. And you see the request times are up to half a minute. So what happens to the application? Nothing. You look at CPU, and now we added a metric for open files. You don't see that anything is happening at all. And the reason is that stuff goes to Frankfurt. You see response times from Frankfurt are like 200 milliseconds at the most. And the queues never really grow beyond 150, so we're all good. So that was great, but I still had this feeling that, well, what happens if, surely there has to be some situation where both of the kinesises are screwed. And sure enough, one day, or to be more accurate, one night, my colleague Magnus gets the phone call from PagerDuty, and he runs to the dashboards, and this is from his incident report. He chose this to illustrate what the dashboards were showing him. It was just total mayhem on every front. Every dashboard was screaming, ah! And it turned out that what happened was that network in was fine, network out was broken. So we get to receive all the events, but we can't send them anywhere. And this was an AWS screw-up, basically. So here's request times to primary and secondary. You see they're up to 3 minutes, 5 minutes when going to Frankfurt. This can't work, right? That's just never going to work. So we see here, that's the spillover queue. Events are going to disk, but application survives. You look at the number of requests we're handling, it's fine. You can't see the impact at all. What you can see is that something happens after the incident ends. Suddenly, we're writing much more traffic. What's going on is that there was a bug in the thing that was feeding back from disk, and if the JSON events that you were reading happened to exactly fill the buffer, it would never finish reading the buffer. It would just keep reading the same event over and over and over and over again. So that single event got sent a few 100 million times, unfortunately. But apart from that, it was great. And this illustrates what I was saying about the emergency code, right? The emergency code runs once every other month, right? It doesn't get very well tested. It's not like the rest of the application. So the more emergency code you have, the greater the risk is, really. If we look at disk usage, you don't see the incident at all. So once I fixed this rewrite problem, we were good to go. Unfortunately, we still had incidents. Not where the service went down, but incidents where the alarms go off because events get written to disk, and then probe starts complaining because the events are sitting on disk in collector, they're not arriving. And people wake up, and they run to the dashboards, and they see, oh, it's in spillover. oh, now it's being sent from spillover, everything's working, they go back to bed, but of course, they were woken up for no reason. So what we did was to add 4 writers. And that's enough, it turns out. Then even if both of the kinesises are slow, it will still handle it. The other thing we had to do was, you saw from some of these here, when you have a request that's taking 5 minutes, that's your writer thread sitting there for 5 minutes going, it's not doing anything useful, right? And chances are that the packet got lost, and if you just try again, it's going to work. So you're wasting precious time here. It's better to time out and try again. So in the code, we set the timeout of, I think it's 15 or 5 seconds, so that if it gets no response within that time, it's going to try again. And that makes a big difference. Here we have the November 11th non-incident, where we fill up the first queue, we fill up the second queue, we fill up the third queue, and we don't fill up the fourth. So you see spillover at the bottom is flat. So this is where the having 4 writers solves the problem. And yeah, I didn't include it here, but if you look at the request times, now they're suddenly capped at the timeout. So that makes a big difference as well. This thing is still not perfect. We shouldn't be parsing the JSON in the collector. That uses about 20% of the CPU. So we could save a good bit of CPU usage by just leaving this until later. So what we really should be doing is we should take the extra fields, stuff them into some binary format, add the JSON blob, and then send all of that, and let somebody later on sort it out. That's a bit involved, so we're not doing that yet. The second stage behind Kinesis is a trivial application, really. It's just a glorified CP. The data in Kinesis lives only 24 hours. So if something goes wrong, we have 24 hours to save the data, basically. Therefore, we want to be sure that nothing goes wrong, and that's why this application is so simple. The only thing it does is read from Kinesis and write to S3. And Amazon provides a library that makes it easy to read from Kinesis. Actually, reading from Kinesis is actually a difficult problem because you have, in our case, you have 50 shards. So there's actually 50 separate streams. And there's a variable number of nodes that's reading these. So doing the coordination so that you know which node is reading what stream and how far it got, and now another node is coming, so we need to rebalance. All of that is taken care of by this KCL library, unfortunately, because that would be the interesting part to write. That's the problem with software reuse. Other people get to solve the interesting problems. AWS has a lot of API limits everywhere, and everything is rationed. So you say, I want this many units of read or write or whatever, and if you then go above it, Amazon will just cut you off and say, no, you can't get this much. And KCL will only give you 10,000 records each time it reads. That's the max. But actually, when we look at it, we never get that many records. There can be 100 million records in the stream, but we never get as much as 10,000 per call. It turns out there is some undocumented API limit. So I did an experiment where I wrote a lot of small records into the stream, and then normal-sized ones. And then when you read it, you see here that as long as it's reading the small ones, you get full-sized batches, and then once it hits the big ones, suddenly you get small batches. So there's some limit on the number of bytes. What the limit is, we don't know. But we had a case where tracking was was duplicating a field in the events because it was doing an event format change. And they were giving people time to switch over to the new field name. And now suddenly, when the events were bigger, we couldn't keep up with the stream anymore. This is the metric showing how far behind the tip of the stream we are. So we changed how long we would sleep between each time we talk to Kinesis, and you see the result. When you deploy that, the problem goes away. So it's a one-line change, but actually working out that, oh, there is this undocumented limit, and that's what's causing this, because this other team changed what they did. Aha, we have this setting, maybe we can tune that, and seeing, yes, okay, that solves the problem. That's actually the job, not the code change. Yeah. The people processing this stuff, I'll talk very quickly about how they do it. They're using something called Spark, which is basically a Hadoop replacement. Writing Hadoop code is painful, basically. It's a very nasty API. Spark, on the other hand, is pretty neat. Here's code that will load a set of Parquet files from S3. That's the val df line. Then we pick out one column. That's the ID of the site that's sending us the data. Then the map line turns that into two columns, one with the ID and the other with the number 1 for every row. And then we do a reduce by key, where if the IDs are the same, for 2 rows, we turn it into 1 row where we add together the numbers, and we just reduce as far as we can. What this is doing is it's counting the number of events per provider ID. Just the mapping step in Hadoop would be as much code as this whole slide. Now here it's, you just say, take the ID, give me a tuple. So this is much, much easier. And this will then spread out over as many worker nodes as you've set up and run in a distributed way. We have a lot of these Spark jobs because the storage writes to S3, then comes the anonymization, then comes the thing that splits up hourly batches for each of the sites, and then come all the data science jobs behind that. And typically you have a data science job that's extracting something that they use, a feature, and then you have the actual training job behind that. And these all depend on each other. So to manage that with restarts and do I need to run this job so that I can run that job, we use something called Luigi, which was developed by Spotify. And that lets you write stuff like this. I know this looks complicated for something that's basically just a dependency, but it has to be code because one job can depend on, let's say you have a job that's doing statistics for a whole day. That will then depend on 24 hourly batches, and you basically have to use code to express the combination of the parameters, basically, how they depend on each other. So although this looks complicated, it's not actually that hard. Luigi is not perfect, though. It doesn't have cron. So you have to use something like cron to start the jobs. There's only one master. And unfortunately, Luigi has no idea what resources we have. So it can't schedule the jobs optimally, unfortunately. So we've set up a internal tool for running jobs where basically what you do is you take your Spark job, you turn it into a jar, then you add the Luigi stuff and some configuration, and you zip that up. And then there's a command line tool where you say, Nox job deploy. So you're just saying, take my job, run it. And then Luigi will it will start up when it should. Luigi will check that it has run. If it hasn't run, it will only run once, stuff like that. And then you can ask, what's the status of my job? Kill it. Don't run my job anymore. What jobs exist? And that kind of thing. So from your laptop, Nox will send the job to a system called Crane. Crane takes care of talking to a Mesos cluster, setting up your job in Kronos. OK. Then Kronos will start the jobs. They'll talk to the Luigi server, talk to the Spark master, blah, 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 blah. And it used to be that people had their own clusters for doing this kind of thing. That becomes very, very wasteful because a lot of the time the cluster isn't doing anything. And when you have a lot of data science people, this starts costing serious money from AWS. So we've switched to a shared cluster. That saves quite dramatically how much money we spend. The trouble is now we have a shared cluster. Suddenly you get told that, oh, actually, personalization is having a hackathon today, so there are 3 times as many jobs as there used to be. That's why your job isn't running. So then somebody has to sit there and scale this thing up and down and look at the jobs. And actually, this job is using unreasonably much memory. Can you do something about that? And yeah, this coexistence is not painless. We can put it that way. OK, we have 9 minutes. I'll do one more thing before we finish up. This is I'm talking about this because it's a nice little detail. So one day, my team lead comes to me and he says, we have to make an endpoint in the collector where you only say 200 OK if you've actually written the event. And the reason we have to have that is that there are people wanting to send stuff from back-end systems. Basically, the ad sites will send us the contents of all the ads that are created so that the data science people can have copies of all of the ads and do analysis on those. And we do the same thing with the news articles, basically, and videos and images and all kinds of stuff. But these events we can't lose. And they're being sent from servers, so the server can always retry, right? So here there really is a use case for only saying OK when the event is actually written. But that takes us to this solution, which we've already tried, and we know it doesn't scale. So what to do? I figured, well, there aren't that many back-end events, right? So what we could do is throttle it. And just make sure there aren't too many of these at the same time. And if there are too many, we just tell them, go away, we're overloaded, come back later. With servers sending, so it should be all right. So then I did an experiment. Just count the number of requests that are in progress. If there are too many in progress, we say, go away. And then I try it, and it turns out we never have more than 2, which is a bit mystifying. And it turns out that what's going on here is that there's basically 2 kinds of web servers. Apache and Tomcat are worker-based, so they have either a set of worker processes or a set of worker threads that gets allocated in advance. And each one of those threads or processes will take a request, do all the work to finish it, and send the response, and then pick a new one. And of course, they won't be using the CPU all the time, right? Because there will be blocking stuff in here. So then what you do is you set the number of workers so high that there's always somebody who has work to do, so that you're managing to use up the CPU anyway. But we weren't using that kind of web server. Netty doesn't work that way. Netty was, in fact, event-based. And that's where you have a very small number of worker threads, typically fewer than you have CPUs. And these threads will use interfaces that let them look at each of the connections and then always pick a connection where there is more work to do. So they're just switching very, very rapidly between the connections where you can make progress. And this sounds like it should be really slow, but it's not. It's actually much faster. And the reason is that you don't have so many threads, and thread switches are actually very expensive in the kernel. So this winds up being much more efficient. So this is why we never had more than 2 requests going on at the same time, because Netty only has 2 workers. And then when we look at the framework that we're using, it turns out that when I say response status 200 and return that, that's not returning a response. It's returning a future. And this is how I communicate with Finatra to tell Finatra, did I finish this request or did I not finish this request? Basically, if the value of the response isn't filled in, the future, if it's not filled in, that means I'm still working on it, right? So Finatra will keep looking at this, and then when the response arrives, OK, we send the response, we close the connection. So that means I could do something like this. This would be the canonical way of dealing with this. You set up a thread pool. Each request or each event that comes in, you just hand it off to the thread pool, and you send back a future to Finatra. And when the thread pool has sent your event, it fills in the future, and Finatra does the rest. This is the canonical way of doing it, but now we're back to each event being a separate request. That's bad. the whole point of using an event-based server was not having a lot of threads. And now we're back to a lot of threads. Plus, we get a hard low limit on the number of simultaneous requests, because we can't have more of those than we have threads, right? So, but then when you look at what is actually a future, people think of it as being associated with threads, but it's not. It's actually about as simple as anything could be. It's just a wrapper object that lets you check whether a value has arrived or not. That's it. That's the whole thing. This, of course, only makes sense when you have multiple threads, because otherwise a value isn't suddenly going to appear out of nowhere. But there's nothing thready about a future at all. So there is a is done, and you have gets you the value, and then there's a few more variations on those, but that's it. So I realized we could actually do something a lot smarter. We set up the endpoint here. It writes to the same kinesis writer that we've always used, but it adds a callback. It sends in a function that gets called when the event either has been written or it failed. And then inside the kinesis writer, the queue now has an extra field, which is the callback. So some of these events have callbacks and others don't. And then what we do in the actual code is when we hand in the event, we give it a function that gets called with a success if it's failed or succeeded, and that fills in the future. So basically what happens is we're accumulating all these open connections here, and then the kinesis writer tells us when we're finished, and then we pass it on to Finatra, and that's it. So we can do the whole thing with no extra threads, no extra moving parts, nothing. And no hard limit on the number of simultaneous requests. OK. So I need to spend 2 minutes on this slide if we're going to fill out the talk. Yeah. This is what I'm doing at Schibsted. We're still getting started up. The organization is a year and a half, pretty much. But it's actually beginning to work. The Norwegian newspapers are, thanks to the experiments that the data scientists are doing, they are now increasing the number of digital subscribers quite a lot. So the Norwegian newspapers are starting to make money, so that's good. But we're only just getting started. So if this sounds like something interesting, you know where to. You can talk to me, or you can talk to Schibsted. The Stockholm office is just 200-300 meters that way. Yep, that's it. Thank you.